All right, here's part 2, 13.5 Q, and your notes right here. So this is what I'm going to show you now. This is the part that more of the homework is going to cover, and calculation, and boy, there's a lot of stuff here that can be either in a multiple choice on the AP or calculation. They've done all kind of things with this. And it's the last thing we do before we get to the big stuff, the big calculation stuff. All right. Let me see. I have to always cover up my computer so that to try to keep any chalk dust from hitting it. I don't know. Not cover it, but just block it. Don't want to smother it because it's getting overheating. Okay. All right. So here it says predicting the position and direction of equilibrium reactions. All right. Oh, well, here's just one thing, just a kind of a general little tactic or knowledge you can get from this. It says here if the K value, number one, given a constant, if the K value constant is large, equilibrium will lie far to the right position. If it's small, it lies far to the left. And I'll show you what we mean by that. Like, for example, look at letter A. And it says, given the following K values, where will the equilibrium position lie for these reactions? All right, number one, it says you have it's CH3COOH breaking up into H plus and acetate. Now again, we'll see this more in the next chapter. So there's a couple of different ways. You may have remembered, I just showed you another video. I showed you this reacting with water to give you H3O in this, but this is another way to write it down. The H breaks off, and you're left with acetate behind. So it says the Ka value for this is equal to 1.8 10 to the negative 5. So what it tells us, we say the equilibrium position. What that means is this number, is this concentration at equilibrium? If we're at equilibrium, are the amounts of this greater than or less than the amounts of these? What's greater, the products or the reactants? That's kind of what they're saying. And remember, whenever you write a K expression, it's always products over reactants. And so it would be, the H plus CH3COO over CH3COOH. So what it tells us, where is this most likely, if you get this number right here, to get this number, Ka, is it going to be a big number divided by a very small number? Or is it going to be a very small number on the top divided by a very big number? So like if your numerator, denominator, which one is going to be larger? To get a really small number, then that means that the bottom number should be very large. And the top should be very small. Both of these should be very small. A very small number, like a number like, take a small number like 1 divided by like 800,000, and you're going to get a very small point, 0.0000008, whatever that is, very small number. On the other hand, 800,000 divided by 1 is a really big number, 800,000. So if the bottom number is large, then what that means is the equilibrium is on the left. It lies to the left. So that could be a multiple choice question, or probably even they'll give you like all these values like Ka, Kb, Ka, Kb, Ka, Kc. In which of these does the equilibrium position lie far to the right or to the left? Or it could be multiple answers, multiple choice things, multiple. Okay, for this one, number 2. This is the KSP value, 1.6, 10 to the negative 10. Now, what this tells us is the same thing. Here, it would have to lie far to the left. AgCl gives you Ag plus and Cl minus. Now, this also makes sense because, now this is a solid and these are the aqueous. But what it tells us, these are in equilibrium with the solid. Even though the solid is not mathematically in that, it is part of the equilibrium system. Okay, so this must be, I know it's kind of hard here because you can't think about the division here, but obviously these are very, very small numbers. So to get a small number, remember, you can also write down what it would be, the expression, the KSP, AG plus times CL minus. So all I'm doing is multiplying this. If I multiply two numbers and I get that, then these must be pretty small numbers, okay? So those are really, really small. That would just tell us that these are really small and that's really large. Also, in every KSP, if you want to know, KSP is only done for a chemical that doesn't really dissolve in water that well. Like we pretty much say it's insoluble, not soluble. So only a little specks, just little bits of this are dissolved. And when you put the molarity of that times that, you get this really small number. So it's, almost not even... Okay, so anyway, equilibrium would lie far to the left on that one as well. And then here's the last one. It says for HCl, going to H plus and Cl minus, it is K. It says, it should say Ka. That's a misprint in the notes because it's an acid. Ka is equal to 1 times 10 to the 6th power. So what's going on there? Is this a really small, really large number? This is a very large number. That would tell us that these are this over that. These are very large. That's very small. Remember, the Ka for that would be, if you're trying to answer this question also, because it could be like a short answer essay question. You write this expression out. You say, this must be very large, and that should be very small. Very, very large. A lot of that, really, and very small amount of that. And that's true. In fact, you might remember that HCl is a strong acid. And what that means is we assume it completely breaks up 100%. And it doesn't really 100%, but it almost does. So see, remember, what are the 6 strong acid? HCl, HBr, HI, H2SO4, HNO3, and perchloric HClO4. If it's not a strong acid, then it's a weak acid. All the weak acids are like this one. This is a weak acid. They all have very small Ka values, but the strong acids will have a very large number, 1 times 10 to the 6th. That means that in the acid, almost all the particles in this equilibrium, if this is a cup of HCl acid, almost all the particles in here are H plus and Cl negatives, and you have only a little bit of HCl molecules that are not broken up. That's what that means. Almost all of them are broken up, nearly 100% dissociation, they call it. Okay. Now, Q, let me go to this. Oh my goodness, it looks like I do have a little section right here. I wasn't sure if it was in the notes or not, but it is. And I'll talk about that. I guess I am going to go over this in a minute. It says Q. What in the world is Q? Q stands for the reaction quotient. Now, it's called a quotient because really, when you think about a Ka value or a Kb value or a Kp value, it's always one number divided by another. A number divided by a number is the quotient. So, what it is, I think of it this way. Think about what the optimal weather is. Like say, this is the best weather outside. It's like, maybe for you like at warmer, like closer to 80 degrees outside, 78, 79, almost 70, right around 80, 81. That might be great. They might say, this is great. I can wear shorts, walk around, nice weather. Okay, well, if it's really, really cold, what do you need to do to get to the nice weather? Or if it's really, really, really hot, like 110, the desert or something, and you want to get cooler, you want to get back down to into the 80, low 80 or whatever. Well, Q is kind of like the weather report. Where are you compared to perfect equilibrium? Where are you? Are you too far to the left or too far to the right? Where are you? Okay? And what has to be done to get to equilibrium? So Q is a mathematical way to kind of like say, here's the current weather report right now, weather state, and are you perfect? Are you at equilibrium? Or are you not? Are you above or below? Well, I'll say left or right. So here's how it goes. There are some little, like always, some little things here. You have to look at this kind of after I go over the math. But I'll just tell you this. If Q and K are equal, you're at equilibrium. If Q is less than K or greater than K, you're not at equilibrium. And something must happen to get to equilibrium. So I'll show you what I mean by this. I probably won't do all of these, but, well, I don't know. Let's just see. N2 and 3H2 gives you NH3. Two NH3, right? Yeah. Did I say 3? Okay. For a system at this position, now what we're doing is like saying we have these 3 gases mixed together, and we know that the K value is 6 times 10 to the negative 2. At this temperature that they said 500 Celsius, okay? So we're at 500 Celsius. The K value for this reaction is 6 times 10 to the negative 2. So it already tells us right now that's kind of a small number. So that means that this must be a smaller number and that must be a larger number. You know, so the equilibrium position lies more to the left. That means more of the material is on this side, the bigger amount. That's all that really means. Doesn't mean a whole lot here, but let's just calculate this. It says, but let's just say N2, NH3, and H2. I'm going to plug these numbers in and calculate what we would do in the K expression. So, you know, the K expression would be K equals NH3 squared over N2 to the first H2 cubed. All right. Now, if I were to be at equilibrium, then all this number and that number and that number, when I plug them in from letter A, okay, this is B part A, kind of weird, B part A. If I plug in those 3 numbers and I get this number right here, that means it's at equilibrium. If I don't, it's not at equilibrium. So when we plug the numbers in, we call that Q. So we're going to say, all right, for NH3, the number is 1 times 10 to the negative 3. Now I've really got to make sure I don't plug in the wrong numbers here. And it has to be squared. That's NH3. N2 is 1 times 10 to the negative 5. And the other one is 2 times 10 to the negative 3. That's right. And we have to cube that one. So there's a lot going on here with your math. You might have to pause the video or whatever, and make sure I can make sure I get it right. 2 times 10 to the negative 3 cubed. Then 1 times 10 to the negative 5. It looks like 8 times 10 to the negative 8 is what I get. 8.0, 10 to the negative 8. Now let me quickly try it again, okay? Because since we're not here, and I hope I plugged them all in right, okay? I just messed up, oh boy. Okay, it looks like I might have done it wrong. 2 times 10 to the negative 3. I'm going to cube that number. Then I'm going to multiply that as 1 times 10 to the negative 5. Oh, and then I had to do it right. No, it's wrong. It looks like this was the, I forgot to, looks like it's 1.25, 10 to the 7th. This is why I need my students in class to be helping me with this. This is ridiculous doing this tedious math. I wish I could pause you guys on here for a minute so I could check this without you having to see this. Okay. But you can go forward. You can just scrub forward on the video. Okay, that looks like it is the right answer. 1.25, 10 to the 7th. Okay, so are we at equilibrium? Does this number equal that? No, it is not. Is it now, we ask, is it greater or less than that number? All right, system is not at equilibrium because Q is greater than 6.0, 10 to the negative 2. Now, because it's greater, then does it ask you, okay, predict the direction at which the system will shift. All right, which direction will it shift to get to equilibrium? All right, system is not equilibrium because Q is greater than that. To reach equilibrium, the system will shift. Well, how about that? We'll say that. The system will shift, okay, in a way, you have to make Q smaller. It's too big. Q has to get smaller. So think, if this number has to get smaller, overall, Q must get to be a smaller number. Does that mean the top's going to go up or down? That means the top is going to go down and the bottom is going to go up. So it's going to shift. Material that was in the top part of this, the numerator will decrease. You can even say that. Numerator must decrease. The system will shift to make Q smaller. All right, the numerator must decrease, and the denominator must increase, until Q equals K. So what does that mean in terms of direction? So if this goes down and that goes up, that's why I told you, I sometimes tell people to just draw a little arrow to help themselves. Material's got to go from this part to that part. From this part to that part. That means from products to reactants. It's got to shift left. The system will shift, and I can put it there, left. Yeah, I'll put it there. I could have put it at the end. Sometimes I'll put this first, and you saw me, I was showing you how to think through it instead of just memorizing it. But it will always be true. If Q has to get smaller, you always must shift to the left, okay? If Q has to get larger, you'll always shift to the right. But it's better to completely explain it. And you can even say the numerator must decrease, the denominator must increase until Q equals K. Since Q is greater than K. Since Q is greater than K, the numerator must decrease, the denominator must increase until Q equals K. That's always true when Q is larger. So the system will shift left to make Q smaller. Okay, kind of wrote that in a weird way. Well, you know what? I'm not going to do the other examples of those, but I'll just tell you, if Q had been smaller than K, it's just the opposite. If Q is smaller than K, then you'd say it would need to shift in a way for the numerator to increase and the denominator to decrease. If Q is too small, it must shift from bottom to top. Take some stuff off the bottom and make it on the top. The mass on the bottom, or molarity on the bottom to the top. Material. So going from bottom to top means going from left to right. So that means that this has to increase and these have to decrease. That will cause Q to get larger. So this is a good example. I'm not going to work through all the B and C ones. I'll let you do, I think you'll do a couple on your paper. And of course, if it comes out to be exactly that number, then you're at equilibrium, and you'd say it would not shift at all. So I'll talk about this in our class. I'll do an example of this too one more time too. But I don't want to take a whole lot on it. Now, that's just about it. Let me just show you. This is the other part that I said it really comes in the next chapter. And now, maybe I'm going to have to go back and tell you to do it later on. But it said, potassium chloride and silver nitrate are added solutions. Will precipitation occur in each of the following? So maybe I'll do one of these for you. Okay. AgCl gives you Ag plus and Cl negative. Well, here's what you're saying. You're putting in silver nitrate and potassium chloride. Now, remember, potassium chloride and silver nitrate are going to react, and this will be a spectator ion. All group 1 and all nitrates dissolve, right? So you would get silver chloride solid, precipitate, and you'd also get KNO3. But all we care about is the silver chloride. Now the silver chloride will break up into these two. But do you have enough silver and enough chloride to precipitate? Well, that's kind of where Q comes into play. KSP equals 1.6, 10 to the negative 10. So here's how it goes. Let me write the KSP expression. KSP will be silver molarity times the chloride molarity. This is an important thing. This is very important, but it really comes in the next chapter. But it's on the worksheet here, and I'll just tell you. I'll tell you this. Okay, if I multiply these two numbers and I get this number, or that number or greater, then that means it will precipitate. Okay, so if Q equals K, if Q is equal to K, or if Q is greater than K, precipitation occurs. Now here's another weird thing. What if I multiply these two things and it's smaller than that number? If I multiply these and it's smaller than that, what it tells me is there is no solid at all. You just have these in a solution. So you could have these two things dissolved and not see any solid. It wouldn't be an equilibrium because there's no solid. Okay, so we'll do the first one at least here. It says for number one, we'll just do one of these. If silver is 5.3, 10 to the negative 5, and if the chloride molarity is 3.4, 10 to the negative 9, okay, let's just multiply those. So 5.3, 10 to the negative 5 times 3.4, 10 to the negative 9. I get 1.8 times 10 to the negative 13. Okay, so Q, actually, when you're calculating Q, you write the KSP or the KA. I think I showed you a moment ago, but then you just rename it Q, as you're doing your math. So obviously, this is not equal to KSP, and in fact, it's much smaller. So because it is smaller, that means that you don't even have any solid present at all. You're not in equilibrium. There's no solid at all. No precipitation occurs. Now, if I did another example after this, well, if Q is equal to K, now you will have solids. At least a speck will precipitate if it's equal. Or if it's greater than K, then the precipitation occurs. Okay, so in fact, if it is greater than K, then what's going to happen is it's going to shift to the left. Material is not going to stay dissolved. It's going to form a solid. That's what it means by precipitation. So you're going to form more solid if Q is greater than K, until as you move to equilibrium, it will shift to the left so that Q can get smaller. Okay, until it equals K. All right, that's all I'm going to say. So do those problems, and I'll see you later. Adios.